All right, hey everybody. So yeah, I'm Spencer. Been here at Temporal for a little bit less than 4 years, so relatively early employee. I'm the main developer for the core Rust SDK, which powers our all of our ones that aren't Go and Java. So that's Python and TypeScript and .NET and soon to be Ruby. Big fan of just like using lots of programming languages, and that kind of fit really naturally into this job. So today, we're going to talk a little bit about kind of like what it is that temporal SDKs do on a sort of fundamental level. You all know that they let you write workflows, and ideally all of you know what workflows are. That's why you guys are here. But how does temporal actually guarantee what we call durable execution, right? What you guys have probably heard about a lot over the course of this conference. And the magic to making that work involves some like pretty cool techniques. So today we're going to talk about those internals. We're going to learn a little bit, hopefully, about like how we make that magic work. And really, the point of this talk is like just to satisfy your curiosity, really. But perhaps it'll also help you learn how you can maybe avoid doing things in your workflows that might be bad, or like better do things that might be good. Yeah, so let's kind of jump right in. Durable execution is sort of like our name for the promise that we make to all of you that you can write workflow code without needing to think about what happens if you lose progress somehow. So more specifically, what that means is the state of your workflows is never lost for like some reasonable definition of never, right? Like if the persistence that backs temporal somehow goes away or is corrupted, like, well, okay, we can't do anything about that. And how do we make this work? Like we don't actually like save the state of your workflows somehow. A lot of people, when they first encounter the product, they have this assumption that we like snapshot memory or something, and that's how it works. We don't do that. That would be kind of slow. It would be like error prone in a bunch of ways that like aren't obvious and would be really difficult to recreate state. And like what happens if you move from like one architecture to another? There's all sorts of like complications there. So we don't do that. What we do is we have to be able to recreate state deterministically. And in order for us to accomplish that, we store this append-only log of events for every workflow. And that's the workflow like history that most of you are probably familiar with when you like go into our UI and you look at the list of all the stuff that's happened. So the biggest challenge that SDKs face implementation-wise, sort of besides just making nice APIs for all of you guys to use, is that we have to turn that event log, that like history, into the state of your workflow code. And we do that by replaying it, right? So hence the name of the conference. And that's also, incidentally, why we require your workflow code to be deterministic. So like show of hands, how many of you have run into a non-determinism error? So that was like even more than I expected. Yeah, so pretty common thing to do. So let's move on. Oops, can't actually talk about this yet. We don't really know enough to tell you how replay works yet, so let's move on to the next thing. How history is constructed. Oops, still don't know enough to talk about this yet. We kind of need to know how workers actually process what we call workflow tasks first. So let's talk about that. Good, we can actually talk about this. Workflow tasks are sort of like the fundamental unit of progress for workflows. So anytime that your workflow makes progress, it does that because it's processed a workflow task. And workflow tasks contain either a partial amount or all of the history of your workflow, along with like potentially some other information, like maybe queries, and there's other little bits of bookkeeping. But the main thing is that there's like some chunk of history. So let's take a look at an example. This is, if you guys have looked at history at all, you're probably pretty familiar with this sort of preamble. The first workflow task in your history is always going to look like this. If you want to be pedantic, there could potentially be some like signals in here between like events 2 and 3. But the important thing to understand is that the first workflow task that you process, the first thing the worker sees is like started and scheduled. And then when it's finished with it, you're going to end up with started and completed right next to each other, 3 and 4 here at the end. So what's going to happen, the SDK is going to receive that task. It's going to process the history, of which there's not a whole lot so far. And then it's going to like do some stuff that we'll talk about a little bit later. And eventually, it's going to run your workflow code. And after your workflow code has run, it's going to respond with what we call commands to the server. And commands are things that you're all familiar with, like activity is a command, starting an activity is a command, like running a timer is a command, running a child workflow is a command, so on. Let's look at some code. So here, I've got a Python, like a super simple Python workflow. And so the first time that a worker running this Python workflow code receives a task, it's eventually going to call this workflow run method, right? And what's going to happen as we go line by line is we're going to run this execute activity command, well, not command, function, which is going to end up creating a command. We're going to run async io.sleep, which we have done magic to in the internals it doesn't actually do async io.sleep. It creates a timer command. You'll notice, for those of you that are familiar with async Python, but if you're not, don't worry. Like, we're not actually waiting on these here, right? We're just running them. And then we get to this async io.gather line. You can see we have an await there. So like, we're actually going to wait on that. And for those of you who aren't familiar with Python, all gather is saying is like, I want to wait for both of these things to complete. And so when we do this, interestingly, it's actually when we hit the gather line that this happens, but you can ask me after for some more details on that. But what happens is we're going to sort of buffer the command to schedule an activity from execute activity. We're going to buffer the command to start a timer from async io.sleep. And then like, we're stuck. Like, we know as the authors of the SDK, the ones who are running this async run function, that you're like stuck here on gather. It can't make more progress. Therefore, it's time to like yield control back to us. We wrote those activity and timer commands in the buffer. So what we're going to do is going to collect them. We're going to respond to the workflow task to server with like, hey, we want to schedule an activity. We want to start a timer. And that's sort of like, that's the whole life cycle of like completing this first workflow task. So now we know a little bit about what a workflow task is. We can go kind of back up. And we can talk a little bit about how history gets constructed. So we know that workflow tasks contain history. We just talked about how they are responded to with commands. And it turns out that every command that we have, like every command type, also gets turned into some like corresponding event, right? So I call those like the event dual of a command, or sometimes you can call them command events. We don't really have a super well-defined name for that. But Temporal Server, when it receives these commands, it's going to write down the dual version of the command. So in this case, you can see I'm talking about like schedule activity command. That's the thing we would have sent back with the workflow task response, becomes an event called activity task scheduled, which like you guys might be familiar with from the history. And the server, when it does this process, it's also going to like go do something with that command. In the case of an activity, that would mean things like dispatching activity tasks for workers to go run as activities. In the case of a timer, it's like writing down some entry in a database and keeping track of the timer so that we end up firing it later. And then eventually, something is going to cause new events to be added to history like externally from the workflow, right? So the activity might get completed, the timer might fire, and when that happens, Temporal Server is going to create a new workflow task because like there's like new information that the workflow needs to know about, right? Like something external happened, and therefore we need to go like wake up the workflow code and see if you guys wanted to do anything like in your business logic with those results. So let's go back to the example. Here's the like full history for if I finish that workflow. So we can see the like duals or like command events that I talked about, right? We have activity task scheduled and timer started. Those are numbers 5 and 6 here. And we also have like their like consequences, the sort of these like external events I was just referring to, right? Which in this case is number 8, the task completing, and number 12, the timer firing. And you can see that after each one of these like consequences, a new workflow task gets created and gets processed. And in this case, we have this sort of like one-to-one correspondence, but in the event that they happened like really close together, we might only make one workflow task, or like say you don't have any workers around to process a workflow task right away, there might be like many such events before we actually end up like, you know, sending out a workflow task and having some new worker process it. But in this case, there's one for each of them. And so this sort of like whole cycle just continues over and over until the workflow gets complete, right? Like new workflow tasks get created as the result of something happening, worker processes them, responds with commands, something else happens again, new workflow task gets created, and like this is the cycle of life. So let's continue with our worked example here. The first consequence, the first sort of external event that happens is this activity completing. So like we're going to see what our code's going to do after it picks up the task that contains that. OK, so we go back here. We're still sort of like on this same line, right? We're on this async io.gather line. And we know that in this case, the thing that's bound to the variable called myHello, like that future's done. But you know, as I mentioned before, gather wants us to see both of these things be finished. Therefore, there's nothing to do. We're still blocked on this gather line. We're still awaiting. And so the SDK knows after it gets this task, like, well, it's still blocked. Workflow can't make any more progress. I have to respond to the workflow task. So I'm going to respond to it with just like no commands. Like, there's nothing for me to do. User didn't say they want to do anything. Workflow's still blocked. So we send back just an empty list of commands to the server. We say we process the workflow task. So let's go back again to the history. And sure enough, that's kind of exactly what happens, right? We can see on line 11 the workflow task completes, and there's none of these like command events after it. The event at number 12 is the timer firing from before, but there's no activity task schedule. There's no like timer started. There was no new commands, just empty workflow task completion. OK, so continuing on, next consequence is this timer firing in event 12. So another task gets generated. We'll go back to our code again and see what happens. OK, great. Async io.gather can resolve. Like both of these futures are complete. And as soon as we do that, we're just going to be able to keep executing code, right? So like move on to the next line, which in this case is just finishing the workflow and returning a result. This is also a command. Like this also fits our whole pattern. So like returning from the workflow function and completing it is a command called complete workflow execution. So we finish that workflow task. The command that we're sending, and there's only one this time, is to complete the workflow execution. So we send that back up. And you know, sure enough, that's what's happened. Here it's turned into its dual, workflow execution completed, and the workflow's finished. Like, we did it, you know, fantastic. So let's kind of look at it like a slightly different way and sort of reinforce what I've gone over here. We've got a diagram that's like maybe legible for some of you in the front. But we can see again that this sort of repetitive nature I'm talking about is demonstrated in this diagram. We have this big outer loop, which is delineated by this dashed box that goes all around the big colored boxes. And that's the SDK like repeatedly polling server and asking for history. In that green box, we see it's like the bit I talked about where we poll, something external happens to generate a new workflow task that gets created on the line with server. And then in the purple box, we get the response. We apply the workflow history to our state. We unblock all these like awaitable things, which in the case of our Python was these like futures. And then the user code's like unblocked, you know. SDK takes all the commands that got buffered, sends them up to server, cycle repeats. And now we're going to kind of zoom in a little bit to the actual like apply workflow history to state concept. Cool. So we like finally actually know enough that we can talk a little bit with the remaining time about how replay works. So history processing. So in like the previous things I was sort of talking about, okay, we get the history and then somehow your code wakes up. How does that actually happen? So the SDK takes events from history like one by one and feeds all of them into some like corresponding state machine. So there are state machines for every like type of command. There's a timer state machine, there's an activity state machine, child workflow state machine, yada, yada, yada. There's a whole bunch of them. So the SDK's sort of view of what your workflow state is the composition of the states of all of these different little state machines. And importantly, also like what order they're created in. And we'll talk on that a little bit more later. There's a bunch of other there's a lot of other associated bookkeeping, but like the kind of fundamental thing to think about is like basically we have a state machine for every single command you create, and we apply the history events that are relevant to that command, like to that state machine. So here I have our history that we were just talking about on the left, and on the right I have a state machine diagram of the timer state machine as it is defined in the core library, but its definition is like exactly the same in Go and Java, basically. So let's kind of like look at how it works. When we first create the timer, starting up at the black dot here, we exist in this created state, and then we like immediately call this schedule transition, which is going to produce that like start timer command we talked about that's going to end up in the buffer and eventually get sent to server. That eventually becomes the timer started event. So the create state isn't really necessary here, but it just is kind of a useful way to for us to produce the command at the very beginning. And then what's going to happen is eventually at some point when the SDK gets the next task, you're going to see this timer started event in history, and we take the corresponding transition, right? So we take this timer started transition that moves us into this start command recorded state, and then we're going to wait for another event to see what happens, which in this case could either be the timer fired event or cancel, which here is not an event, but is actually something you would have requested to have done from your code, right? You might tell us you want to cancel the timer. So for the curious among you might be sort of wondering, why does start command recorded even matter, right? Why do we need to see the timer started event? Why couldn't we just wait to see if we're fired or canceled, directly from the state where you created the timer, right? Why does this intermediary state exist? And the answer to that is kind of a big part of how we actually enforce determinism. So the reason it matters, the reason that timer started transition matters, that transition where you observe the corresponding event to your command, is that we need to be sure when we're replaying a workflow, as opposed to executing it for the first time, that the code that we're running now is trying to do the same thing, in this case start a timer, in the same spot as what we saw in history. So this is why I mentioned a little bit ago that the order that the state machines are stored inside of the SDK matters, right? Because we have to see the same sequence of commands produced in the same order in order to ensure determinism. Otherwise, you might have changed your code and we wouldn't know that fact, right? So if you intended to do two things that are mutually exclusive with each other, you put them on either sides of a branch, right? But then let's say you came along and just flipped those branches. If we didn't write down these dual events and we didn't keep track of them when we replay, we might just, you might have run the command in one branch once the first time, and then we'd come along and we kind of don't check and don't care. You're in the other branch now, and we say, oh, OK, now we're going to run this one. But that wasn't your intention, right? You meant for them to be mutually exclusive. And so if we didn't do this check, and we didn't see, you're doing something different in the same spot, or you did something that wasn't that before, we can't give you any guarantees. So like you could just do whatever, and your state is sort of whatever, and like all of our guarantees are thrown out the window. So that's why this ordering matters. So how did, like how does that end up? Why did all you guys raise your hand? So let's go back to our example code, and if you have great vision and ability to remember, you might see that what I've done here is all I've done is change the order of the arguments to gather. Everything else is exactly the same. But because of the way Python futures work, they're kind of executed lazily. What this means is that the commands actually get created in the other order than what we did before. This time the timer command gets created first, and then after that the activity gets executed. So, what's going to happen? Bet you guys know. Bam, we get a non-determinism error when we try to replay our history that was done with the other code. So let's focus on the relevant part. Oh yeah, I forgot, oops. Looking on the relevant part, we get this sort of, it's now that I've explained everything, hopefully this makes sense, but if you read this without knowing all that, it probably wouldn't make a ton of sense. We see this line like, timer machine does not handle this event, activity task scheduled. And all the stuff I just talked about, now hopefully this sort of makes a little bit more sense, right? Like the command event, the dual of the command that we observe in history is activity task scheduled, but what you're saying you want to do right now is start timer. Like, those aren't the same thing. Therefore, you probably changed something, or your code wasn't deterministic in the first place, or whatever. Now you're effectively going to perform undefined behavior, and we don't want to allow that to happen. So that's really the heart of how we make all this work. That's how we enforce that your workflow state's always going to stay consistent. It's how you guys can trust that your workflow is going to do the same thing. That's how we offer the magic of deterministic state replay. So, summarize one more time. Let's just reiterate that loop. I think it's a useful thing for you guys to know. Workers get tasks. They process the history in those tasks. Your code gets run. Commands get buffered. They get sent to the server. Repeat that over and over until your workflow completes. And then kind of the key insight about how we make determinism enforcement work, commands always got to be emitted in the same order as they were in the history that you were playing. And that's how we make it go. And that's how we do it without having to do things like memory snapshots or other kind of error-prone techniques that maybe have some other advantages, but also have a lot of downsides. Temporal SDKs do a lot more than this. They do all this fun stuff. You guys maybe use some or all of these features. There's a lot more than would even fit on this slide. But hopefully you guys enjoy all this great content. And that's what I've got for you today. I love feedback. We all on the SDK team love feedback, I should say. We have this guidepost thing that's at the end of the hall by the windows. Go visit us there if you haven't already and you want to ask questions. Feel free to join up on Slack. We've got channels for all the different languages, including core if you want to talk to me about the inside stuff. Check out our GitHub repos, and we love contributions too. Thank you for listening. Please give us feedback. It's awesome. You guys are great. And I think we have a little time for Q&A, maybe? Yeah, OK, cool. So questions. Do we have a mic? OK.
Hey, thanks for presenting this. So the replay bit which you described, that effectively be equivalent of event sourcing pattern?
Yeah, it is. Sorry. So the question was, is replay an event sourcing pattern? Yes, it is. Right. We have an event log. We do stuff with that event log. The specifics of replay are not necessarily what you would think of as event sourcing, but the mechanism is event sourcing. Yes. Yeah. Yeah, that's a great question. When I'm replaying, how do I know which one to match it against? It's the ordering thing. So the state machines actually get created from your code. So when you say, I want to do an activity, that's when I instantiate the state machine, and it just goes into this ordered list of state machines. And so when I then am replaying, I'm specifically looking for the events that are these command events, these dual events. And if the state machine you made isn't doesn't match up with the one that's in that spot in, after the workflow task completion, that's how I know you didn't do the right thing. And then also all the other events get applied to them, and maybe they won't match, and so that's another source.
So when the code runs the first time, you have a list of state machines, or it's being built as you run. How do you know which is the next? Like as you're looping through the events, do you have to like scan down the list of state machines to find the right one?
Yeah, that's a hard question to ask. He was asking like, do I like scan ahead in the list? Like how do I don't have time to answer completely. But yeah, there's like, sometimes I look ahead, sometimes I don't. It's complicated, moral of the story. Pink.
Yeah. You talked about in the Python SDK, you won't send commands off to the server until you hit a blocking call. So you don't like do it in the background or go off and send that and then come back and return control to the workflow. Why do you do it that way as opposed to doing it inline? And is that true of all the SDKs?
Yeah, so the question is, why do I kind of wait for workflow code to block before I then go do stuff? I mean, part of it would be because I just don't know any other way that I could make it not race. In some sense, it's sort of necessary. But beyond that, yeah, I mean, so the other thing, right, is if we didn't run all that code, if we didn't like execute it in a way that was perfectly deterministic, then we might cause these problems for you, which would really suck, right? So like, not only, this was just one example with one serial function, right? But what if you were running a bunch of different routines all at the same time, like what looks like concurrently to you? It is concurrent, it's not parallel, right? So every language actually has its own sort of interesting hooks into that language's runtime. So, we control the Python async IO event loop such that we always deterministically execute coroutines in exactly the same way. And so I can see when everything gets blocked and it's time to send commands back up, and I can guarantee that it always happens in the same order. And so to rephrase your question slightly, it's almost like I have to do it that way in order to make sure everything works. And it ends up being desirable for that reason, if that makes sense.
Just to add one point to that, is the task is pure CPU dependent task. It's never
Yeah.
doing any IO, so it's like instantaneous.
Yeah, that's a good point too. Yemen's saying like, it's already a requirement of workflow code that you guys can't do impure stuff in them, right? Because those things could also be non-deterministic. And then beyond that, we want to make sure it runs fast, so we do things like we make sure you don't take more than a second, otherwise we fail your test for you automatically. There's a bunch of reasons, yeah. Still have time for one?
Just out of curiosity, so you guys have the Rust core running most of the SDKs, and then you've also got the Go and the Java SDK kind of off to the side. Do you guys ever encounter any difficulties with like behavioral consistency or
Yeah.
things like that?
Yeah. The question was, are there sometimes inconsistencies between the Go, Java, and Rust implementations? Yeah, that's why the Rust one exists, right? Like Go and Java actually predate Temporal, right? They were part of the original Cadence project. If we could have all done it from the start, we would have probably just done the Rust one. And maybe if I'm lucky, one day we'll get to port the Go and Java ones, and there'll only be one implementation. But yeah, like that part sucks, right? That's like why we made the Rust one.
What does interop between the SDKs that use the Rust core look like?
Yeah, what does interop with Rust look like? It's basically like a C boundary, right? It's CFFI. There are some nice libraries that we depend on. For example, for Python, there's one called Py03 that makes some automatic bindings between Python and Rust, and is actually very nice because it allows us to do things like call async functions on both sides in a way that's pretty natural. It would have been like a lot of work if that didn't exist. So props to those guys. But at the end of the day, fundamentally, it's a C FFI.
What's the weirdest source of non-determinism you've seen?
What is the weirdest source of non-determinism I've seen? I mean, usually it's ones that users haven't, like I think the sort of user-written ones are usually fairly obvious. The most non-obvious ones are usually like our own fault. Like if you all have used local activities before, it's a nice feature, but they're like wildly complex under the hood to implement. And I've definitely had some fun and unusual bugs that, and at the end of the day, are usually the result of some like weird race condition where some stuff, when you're replaying, like resolves in a different order than it did when you were first executing, and those ones are tough.
When you're comparing the order to the previous order, how is that fast?
How is it fast when we replay?
Yeah, I mean, it seems like, what's the level of overhead that's imposed by ensuring
This
that things are?
is quite small. I mean, when you think about what actually needs to happen, it's just like a bunch of conditions, right? Like, to the point Yimin was making, we already require that your workflow code doesn't do anything. Like, it's just business logic, right? So like, the only thing we need to do is like, go through a list, do a whole lot of conditions, lots and lots of conditionals, but there's no like meaningful compute, right? Like, so really it's iterating through what the end of the day fundamentally is not a big list, at most something with like on the order of tens of thousands of items in it, and then like running your code. So, you know, in something good like Go, something with less overhead. I don't even like Go the language that much, but the replay is like milliseconds, right? It's like a few milliseconds, even to replay a pretty long history. So it's not expensive. All right, I think that's all we got time for. Awesome, thank you.